That happens.
Well, at least nothing wasn't shown yet.
Right. Okay. Well, thank you, Omar, for letting me know through the text channel. Cool. All right. So we are not missing anything because this is the starting point. Um, so what I will also do is to do the same thing as last week, which is basically I'm going to use a spreadsheet on the side to take a look at this. And I believe that spreadsheet is still around. Yep. So this is the spreadsheet of the previous graph. So what I'm going to do is to repeat the headers of these columns. In fact, I can probably just kind of copy all of the columns and onto a separate sheet. There we go. And then just delete how things are initialized and then redo that part. There we go. So now we have a blank slate. And you might want to open up the algorithm so that you can refer to the algorithm. I know the algorithm well enough that I don't need to look at it, but if you want to, you can look at the algorithm as we follow the algorithm. Um, yeah, this is Dijkstra's algorithm because A star requires heuristics. So we don't have an H function in this case. And as a result, it cannot really work with the A star algorithm here. So we are referring to Dijkstra's algorithm of the module that we referred to from the previous class. All right, so the initialization, is we need to initialize the L value for a whole bunch of stuff. Um, and we can see that this A column here is for V. So V starts with S. Okay, in this particular question, the set S consists of two vertices. D and E are both destinations. So this is one thing that Iraj's algorithm does not handle, is to have multiple destinations. And also in Iraj's algorithm, there's a starting point, there's a beginning vertex, but in this particular modified algorithm, there's no beginning vertex. We basically, treat every single vertex as a potential starting point, and we want to find the shortest path from every single potential starting point to a destination. But all destinations are considered equal in the sense that if you can get to one of the destinations, you're done. Okay, so there's no preferences between the destinations. Column B is not used because we only need it when we get to V and W. So we also need to initialize L, which is column D. So column D here. So let me just kind of get rid of. This is fine. It's just the initialization, but the set S has both D and E in it in this case because we have two elements in the set of destination vertices. Column D is the set L. So initially L is going to map everything to infinity except for the destinations. So it is a set that maps D to 0 because D is already a destination. It's also going to map E to 0 because E is also one of the destinations. So from this sense, this example is a little bit different from the other one. But everybody else, like A, B, and C, they are all mapping to infinity because we don't have, they are not destinations. So at the beginning of the algorithm, we are basically assuming that there are no paths from A, B, and C to a destination until we discover a path to the destinations. The set E prime is initialized to an empty set. This is our um, excuse me. So this is basically our solution graph. So E prime is initialized to an empty set. So this is our kind of starting point. Um, and I also misspoke that V is not the one initialized to D. It should be Q, which does not come into consideration until we are almost starting the while loop. All right, so this is all the initialization we need to do. A star is going to have a little bit more to initialize, but in Dijkstra's algorithm, this is all we need to initialize, which is L and E prime. So now that we are going to start the algorithm, we start with Q before the loop. So Q is initialized to the same as S, the set S. So we have D and E in those two in that particular set. Um, and that's the only thing we need to initialize before we get into the loop. Column B is reserved for vertex V, so we have to choose a vertex out of the set Q, and we want to choose the one that has the least L value. And then column C is used for W, which does not come into consideration until we get to the for each loop inside the while loop. So first thing first, we have to pick a V out of Q. So in this case, we can choose either one because the L value of D is 0, but the L value of E is also 0. So since they are the same, we can pick one or the other. It doesn't really matter which one. I'm going to pick E first. Okay. And once we pick E, we have to look at all the incoming edges of E. So we can see that there's only one incoming edge of E coming from B. So we are actually looking at the edge BE, which has a distance of 2. But before we get to the computation of the shortest path from B, we have to indicate that vertex B is variable W here. So now we have, to consider, have we just found a shorter path from B to a destination? The answer is yes, because what we knew about B, or what we knew about the length of the shortest path from B to a destination was infinity, because we didn't even know whether B can get to a destination or not. But now we know that B can go through E to get to a destination. Now, that technically is a kind of not so smart thing to do because E itself is a destination, but it is also not wrong that B can go through E to a destination. And that path is going to have a distance of 2. So as a result, E is going to be, or the L value of B is going to be updated to 2 from infinity. So I just copy and paste it, and I locate B in the set, and then now we map B to 2 because 2 is the length of the shortest path from B to a destination. And we are also going to do a few other things. I forgot one thing here because every time we pick an item out of queue, you'll be in the while loop, but before the for each, we have to remember to take it out of queue so that we don't get into an infinite loop. So I forgot about this update of queue here. But now that we know that BE is a better way, quote unquote, better way for B to get to a destination, we also have to remove everything from B, all the edges starting from B in E prime. But that is not a consideration because E prime doesn't have any edges at all at this point. So there's actually nothing to remove. But now that we know that the edge BE will lead vertex B through a shortest path to a destination, we have to add that to E prime now. So we have BE as an edge in E prime at this point. And we also have to add the vertex B to Q. The idea is we just found a shorter path from B to a destination, so that can potentially impact all of the vertices that has an edge directly going to vertex B, because they might have a shorter path at this point as well. We don't know whether that's the case or not, but that's why we put B into the set Q so that that can be considered at some point. All right, and that's it. Okay, as far as VE being E is concerned, this is the only edge going into vertex E. So now we get back to the outer loop, the while loop. We look at Q, which is non-empty, and then we look at the vertices B and D and see which one has a smaller L value. So out of these two, D has a smaller L value, so we're going to choose D this time. And then every time we choose something out of Q, we have to remember to remove it from Q so that we don't get into an infinite loop. Now we look at vertex D and ask, well, are there any vertices coming into this vertex? Are there any edges? Sorry, are there any edges coming into vertex D? And the answer is yes, there's one. Um, vertex A goes to vertex D through the edge AD, which has a distance of 8. So now we ask the question, did we just find a shorter path from vertex A to a destination? The answer is yes, because we didn't even know that there was a shortest path or any path from vertex A to a destination. Now we do. So we update the L value corresponding to A. Instead of saying that we do not know there's a path, now we do, and the path has a distance of 8 because it is a single edge from A to D. There we go. And we also have to remove all of the edges in E prime that start with A, but there are no edges in E prime starting with A, so there's actually nothing to remove. But now we add the actual edge from the current shortest path from A to a destination, which is AD. And last of all, we add vertex A to Q, so that we have to remember and say, hey, anything that goes into vertex A may now have a shorter path. Okay. So are there any questions about tracing the algorithm up to this point? Okay, I'm not seeing any questions in the text channel. All right. Okay, we're good. So now we go back to the while loop again. The while loop says Q is not empty. We still have work to do. So out of the two vertices A and B, B is the one that has a smaller L value. So we choose B this time, and then we get it out of the set Q. So Q now only has vertex A in it. Then we look into all the incoming edges to vertex B, which there are two. Oh, okay, very good. Um, okay, so we are looking at the incoming edges of vertex B. So there's AB incoming, there's also CB incoming. We can choose either one. I mean, there's no need to prioritize one or the other. So I'm going to choose C first. So now the question is, did we just find a shorter path from C to a destination? The answer is yes. C can go through B to a destination, whereas before we did not even know whether there is a path from C to a destination or not. So the L value of C is updated to 1 plus the L value of B, which is 1 plus 2, and that is a 3. And in E prime, we just have to add the new edge because there's nothing in E prime yet that is starting from vertex B. So we just have to, nope, I take it back. No, vertex C. Okay, I take it back. So there's nothing in E prime that is starting from vertex C, so there's nothing to remove. So we just have to add the new edge. Oops. Okay, so just, okay, there we go. So AD is still here, but now we have to add the edge CB into E prime, and then we also add C to Q. There we go. And now we look at the other incoming edge to vertex B, which is from A. So we look at vertex A, B as an edge. And vertex A had an L value already, which is 8. But this time we just found a shorter path because it is 4 plus 2 this time. So the L value of A is going to get updated. So we go to the L value of A and change that to a 6 this time. But that means, this time we got actual work to do as far as E prime is concerned, because there is an edge coming from A already going to vertex D. We have to get rid of that. But in addition to getting rid of AD, we also have to add AB as an edge. So I'm just sort of replacing AD with AB, but these two are from separate steps in the algorithm. I'm also adding A to Q. Since A is already in Q, it doesn't seem to change, but that update is still there. So now that we're done with CB and AB, we have exhausted all the incoming edges to B, and now it's time to move on to the outer loop at the beginning. Q is non-empty. Now we have to choose one of AC, whichever one has a smaller L value. So out of these two, C has an L value of 3 and A has an L value of 6. So C is the one that we're going to choose. Now we have to look into all the incoming edges of C, and there's only one, which is from B. So we still have to write it here, even though it may not be doing anything useful, but we still have to write it here. So now the question is, are we finding a shorter path from vertex B to a destination? The answer is no, because vertex B already, the shortest path from vertex B to a destination is 2 at this point. So the new path, which is part of the loop, is going to be 1 more than 2. So we did not find a shorter path from vertex C to a destination. Excuse me, from vertex B to a destination. So as a result, this time there's nothing to update. I'm not updating L, I'm not updating T prime, I'm not updating Q, and we're done because there's only one incoming edge from C. Oh, by the way, I forgot to get rid of C from Q, so we have to remember to do that here. So now Q only has one vertex left, which is A, so I have no choice but to choose A as variable V. And now we look into all the incoming edges of A. There's only one coming from B. So we are now looking at the edge BA, and then we ask the question, are we finding a shorter path from B through A to a destination? So if we are going to use the edge BA, which has a cost of 2 to get to a destination, um, A right now has a shortest path from A to B, and then B to E. So that's a length of 6. So if we are going to go from B to A to a destination, we have to add the distance of BA, which is 2. So 2 plus 6 is 8. Okay. So now we compare this length of a path from B to a destination with the other one. Now, the other thing that we also know is, hey, this is a loop, okay? In other words, this is not even a path. But we don't even have to check whether it's a path or not, because as long as the edges have non-negative edge distances, we are not going to form a loop, okay? It's just not possible. So there's no update in this case because, the length of the shortest path from B to a destination was 2, and it still is 2 because the new path has the new not even path has a longer distance. So we also have to remember to update Q. I keep forgetting to update Q, and at this point there's nothing to do, so we get back to the outer loop, and the outer loop says, hey, is Q empty? And the answer is yes, Q is empty. And now we are done with the algorithm. So after the algorithm is done, we need to look at the solution. In other words, what does the solution graph look like? The solution graph has the same vertices, A, B, C, D, E, but the edges are coming from E prime instead of the original E. So we look at BE, okay, and we say, hey, this is a good path, okay, this is the shortest path, or this is the edge, an edge of a shortest path, and that shortest path is going to be from B to a destination. And we also look at AB, okay, and which is this edge here, okay. That is part of the shortest path from A to a destination. And we got one left, which is from C to B, okay. So C to B is this edge over here, so that is also part of the solution. And that's it. Okay, this is the solution graph. The highlighted edges is the solution graph. Then some people may ask, but what about vertex D? The vertex D there are no edges in the solution graph for vertex D. Well, why do we need any? Because vertex D is already a destination. In other words, if the little boy, in the previous analogy, says, "I need to go to the bathroom like really fast now," but the little boy is already inside the bathroom. There's no need to travel, right? There's no need to go anywhere. So that's why vertex D does not have an edge because it is a destination already. So, are there any questions about this illustration of the algorithm? If not, we are going to continue to talk about the A star algorithm. Okay, so the answer is no. I'm not seeing anyone um, asking any question. So I'm going to continue with the A star algorithm now. The A star algorithm is interesting because it is supposed to be a faster, or hopefully a faster algorithm compared to Dijkstra's algorithm. The Dijkstra's algorithm, in the worst case, is um, no more than the complexity is no more than the number of edges. So if you have a really well connected graph, potentially it can be the number of edges. Most of the time it is not, but it can still potentially explore a lot of things that is not really needed. I can show you a graphical representation to explain that. So, but the first thing is I need to get back to the graph module, which is here. And then we can talk about why the A star algorithm sometimes may not be the best idea. Okay, so let me switch back to the tablet view. So, okay, so this is one way to kind of visualize it. So let's just say that we are talking about a single starting point. Okay, so this is my starting point here, and this is my destination, and this is a two-dimensional space. So look at this as Google Map. Okay, you're starting somewhere in Kansas, and you want to get to somewhere in New York City, which is here. All right. So so what Dijkstra's algorithm really is doing a breadth first search. Okay. So Dijkstra, Dijkstra, is a breadth first search. So what it's doing, it's looking around this X, or the starting point, in just starting small, and it's basically expanding a circle in terms of whatever cost what distance we are looking at. So it can be fuel, can be money, can be time. It doesn't really matter what the distances are representing, but it keep expand this circle until we get to the destination. Then you go like, but tech, this is Iraj's version of the Dijkstra's algorithm because we start with the destination. Well, that is true. But if you start with destination, it's kind of the same thing. You start with New York City, and this time you use this as the quote unquote ground zero, and you keep expanding it. Okay, and if you're only concerned about starting, within, from Kansas City, then you can stop here. But you will still be exploring a lot of places where you really don't need to. In other words, you'll be exploring everything in Florida when you just want to find the shortest path from Kansas City to New York City. That doesn't seem to make sense, okay? It doesn't make sense because it's just in the wrong direction. Why would you want to look at, Florida when you just want to get to Kansas City? It doesn't make sense. So this is where the A star algorithm comes in, quote unquote, handy, because the A star algorithm can use what we call a heuristic to guide the search. So now we go back to the notes, okay, and try to take a look at what is exactly a heuristic. So this is the obscure way of looking at a heuristic. It is a function, and the domain of the function is a two-tuple of vertices. So you might say, oh, are those the edges? Nope. Nope, they're not edges. They may be edges. Some of these may be edges, but they're not necessarily edges. Basically, we are just looking at every single way to pair a vertex with another vertex, including itself. And then we map that to the non-negative real numbers, which are basically just a rule of thumbs. So the idea of this function h is it should be inexpensive to compute, but it is always going to give you an underestimate of the actual shortest, of the length of the shortest path between two vertices. So so we can reuse the example, of my current of what we just talked about today, and apply heuristics. Um, so it also has a L value. So the L value in this case is representing the shortest path between two vertices. So this is the actual length. Okay, it is not like h, which is a heuristic. L is the actual length of the shortest path between vertices, at least at a certain point of running the algorithm. In other words, we may find what we thought was the shortest path, but then we found that, hey, this is actually not the shortest one. I can find one that is shorter. Okay. So let's take a quick look at the algorithm first, just so that we understand the major steps, and then we go back in to actually trace the algorithm using a particular graph. So the graph is still represented using the same symbols, which is G equals to VE. V is the set of all the vertices, E is the set of all the edges. We have the same D, mapping the edges to R star. So this time I'm not even bothering to mention it is V cross V, because, well, I think I used E as well in the previous one, so I take it back, because it only has to map edges to non-negative values, because we only want to find distances of edges with D. And then this one is different, certainly different, because we only start with a single start vertex, unlike Dijkstra's algorithm. The A star algorithm only works with a single starting point. And then we use X as our destination because, as they say, X marks the spot, right? So I'm going to use X, as our destination. And then we have a whole bunch of heuristic functions. Theoretically speaking, we want the heuristic function to work with every single way to pair up a vertex with another vertex. But in reality, we really only care about heuristics getting to the destination. So this second V here really only needs to have one single element, which is X in it. Only the destination needs to be in the second tuple. But if you have a complete, heuristic function that can map any vertex to, that can find a heuristic value of the length between any two vertices, that works too. So this is like an overkill of what we actually need. The initialization is a little bit different. We have two functions to initialize in this case. So we have G and F. Okay, these are the two functions. G is the actual length of the shortest path known at a certain point of running the algorithm from S to V. Um, from the starting point to a particular vertex. Okay, that is correct. So S is not even a parameter in this case because S is fixed. There's only one starting point. So G of V is the actual length of the shortest path from the starting vertex to vertex V. F is almost the same thing, but it also adds the heuristic going from vertex V to vertex X. So so getting back to the graph, give me a second to open a new page because I've used up the entire page already. Okay. So the idea is you have one starting point, which is vertex S. You have one single destination, which is vertex X. Okay. So what we are doing is for some vertex somewhere, in the graph. Okay, we'll call this our vertex V. G of V is representing the length of a shortest path. This length here. This is G of V. So G of V is the actual length of quote unquote the shortest path, at least known to that particular point of executing the algorithm from vertex S to vertex V. F of V is including G of V, but it's also including a heuristic estimate of the length of the path from V to X. Okay, so this dotted line here can be seen as H of Vx. So now when we want to look at F of V, it really is the same thing as G of V plus the heuristic value from V to X. That is one way to look at F of V. So using this equation, we know that if G of V is infinity, in other words, we're saying or we don't even know, whether there is a way to go from the starting point to vertex v, then f of v is going to be infinity as well. Okay, so in other words, we can say g of v is infinity, implies that f of v is infinity as well. That kind of makes sense, right? Okay, so now we get back to the module. So the way we initialize is really quite simple, other than the starting point. So the starting point is the only one that has a g of v of 0, which kind of makes sense, right? Because the g of s is asking what is the length of the shortest path from the starting point to the starting point. That's kind of a stupid question, right? Because that path, so-called path, has 0 edges, and as a result, it also has a distance of a length of 0. Okay, the path has a length of 0. But what about f of v of the starting point? Well, that's really just x of sx. Okay, just give me a really rough estimate of what is the length of the path from New York City to Kansas City. Now, if you say, well, but how do we make that estimate, right? You can really just kind of look at um, the straight line. Okay, if you were to draw a straight line, using on a globe, and you measure that distance from New York City to Kansas City. Okay, I don't even know how far they are, just using a straight line. So I'm just making an assumption. Well, we can actually look it up. Sorry, I can't resist doing this. So we just say from Kansas City to New York City. All right, so it shows us the actual length of the route. Okay, and so the actual straight line, which is the gray line here, is that's the flight. It would cost us $68, which is not a whole lot of money if you think about the distance. But we'll just make an assumption that it is 1,000 miles. Okay, if you were to travel on a straight line on the sphere on Earth from New York City to Kansas City is 1,000 miles. So we can use that as a heuristic. Okay, in other words, we know that this has to be an underestimate of the actual distance, but it's okay because we want the heuristic to be an underestimate and never an overestimate. Oh, okay, thank you. So we'll say 1,096 miles. Okay, so 1,096 miles is the heuristic function. Okay, the heuristic function has to be an underestimate. It can, well, I take it back. It cannot be an overestimate. It can be exact. Okay, exact is actually very good if it's possible, but if not, the only qualification needed is that it has to be an underestimate. Okay, it cannot overestimate. So you go like, I know of one magical function that is always an underestimate. What about, turning f of whatever to be 0, right? I mean, 0 is less than or equal to the distance of any edge. That's actually doable, okay? Except in that case, you are not going to utilize, A star basically degenerates to Dijkstra's algorithm. It becomes breadth first search, unguided breadth first search again. So the answer is yes, you can actually use 0 as the heuristic function. You're basically just not utilizing the ability of the A star algorithm to do a little bit better than um, a blind breadth first search when your heuristic function has no information content in it. Okay. All right. So then what does the algorithm do? I mean, what does it do that makes it kind of sometimes it's better compared to Dijkstra's algorithm? So we also have one more statement here, which is initializing the set O, which is sort of like our set Q, but it's not, okay? Sort of like that because it's still representing the frontier of the search algorithm, except this time we are starting from the starting point and not starting with the destination. And it only consists of one single vertex because the A star algorithm only works with one single starting point. And the algorithm, the actual loop starts here. And you can see the loop is also a little bit different because the condition of the loop is not just to say, hey, if O is empty, then we are good, okay? It is a little bit more complex than that. The loop is saying if there exists at least one V in O, the set, such that blah, blah, blah. So that implies that if O is empty, we are going to get out of the loop. Because when the set O is empty, you cannot have any element V that is inside that particular set. So if O is an empty set, then there exists V in O is automatically false. You don't even have to look at anything else. Okay. So if O is empty, we're done. But what if O is not empty? If O is not empty, we still have to evaluate a little bit more to decide whether we can get out of the loop or not. To stay in the loop, okay, to stay in the loop, we want there exists, at least one element in O should have an F value that is less than G of X. They go like, okay, so what does that mean? Well, let's start with g of x. G of x is relatively easy to understand because the g value of any vertex is the length of an actual quote unquote shortest path from the starting point to that particular vertex. Vertex x is the destination. So g of x is really just saying, okay, this is the currently known, this is the length of the currently known shortest path from the starting point to the destination. Now, I have to emphasize currently known, which means it may not be optimal. Okay, it's just that based on the search up to this point, this is the best path that we have found from the starting point to the destination. So we are now saying that, well, at least one vertex in O needs to have an F value that is less than the known, that is less than the length of the currently known shortest path to the destination. That is a long phrase to describe it. But why? Well, think about the other way. Think about the other way around, okay? Think about the case where every single vertex in O has an F value that is greater than or equal to g of x. What about that? I mean, why is that problematic? Well, let's go back to the graph picture that I have shown earlier. F of v is g of v plus h of vx, okay? And g of v is the length of the currently known shortest path from the starting point to v, which is represented by this thing over here. So that means an f of v is just g of v plus h of vx. H of vx is an estimate, and it's guaranteed not to overestimate. So when we combine these two, when we add g of v and h of vx, we are basically saying, hey, if we go from the starting point through vertex v to a destination, the overall path, okay, if we are to find, any path from S through V to a destination, this is going to be, it's the length of that path is going to be at least f of V. Okay, does everybody understand what I mean by that? F of V is a value such that if you find any path from vertex S, the starting point, through the midway point V to the destination X, that path is going to be at least f of v long because of the definition of g and h. Is that part okay? Does everybody kind of grasp that part? If you need more time to digest this, we can kind of pause a little bit. Okay, I'm not seeing any feedback. All right, so I'm gonna make the assumption that everything is good. All right. So if that is the meaning of f of v, then what does it mean when we have something that's like this? So if this is f of v, what is g of x? G of x is basically saying, okay, through the exploration, we found a path from the starting point to the destination. And this is g of x, and g of x, at least at this point of the algorithm, is basically the length of an actual path from the starting point to the destination. So now we ask the question, what does it mean when f of v is greater than g of x? Not greater than or equal to, just greater than, because it's easier to process, just greater than. What does it mean when we say f of v is greater than g of x? It means v cannot be a midpoint between on a shortest path from the starting point to the destination. Let me say that one more time. F of v is greater than g of x means that v cannot be a midway point on a shortest path from vertex v to vertex, excuse me, from vertex s to vertex x. Okay, which is a really long way of saying v is not on a shortest path. Okay, so f of v is greater than g of x is basically saying v cannot be on a shortest path from the starting point to the destination. Now, I did say a instead of the, okay, because there can be multiple paths having the same length. They're all quote unquote the shortest between the starting point and the destination. So that's why I said, v cannot be on any one of the shortest path from the starting point to the destination. Okay, so now we switch back to the algorithm. Now that we have seen a picture, we switch back to the algorithm, and we basically, this condition here is to say, well, if everything in O cannot be on a shortest path between the starting point and the destination, we are done, right? So if we are looking at the map that we looked at earlier, we want to go from New York City to Kansas City. Um, a place in Florida, would basically say, yeah, I'm definitely not on a shortest path from New York City to Kansas City. So it can remain in the set O, but it shouldn't matter because we can get out of the loop if that is the only thing left in O, because that cannot possibly on a shortest path from New York City to Kansas City. All right. So this part needs some, I just explained the while condition. When we get into the loop, it has some resemblance of the Dijkstra algorithm. That is because both are considered greedy algorithms. Okay, a greedy algorithm basically is, you can also call a greedy algorithm an optimistic algorithm. An optimistic algorithm just says, I'm going to pick whatever is the most promising and explore that first. Okay, they prioritize on whatever is the most promising. Dijkstra's algorithm is like that, and so is A star. They just have slightly different criteria when it comes to what is considered the most promising choice. So in A star algorithm, we only use the F value to evaluate, hey, which one should we choose? Okay, we got a whole bunch of stuff in big in the set O. Which vertex seems to be the most promising? In Dijkstra's algorithm, we look at the length of the shortest path from a vertex to a destination, and we use that to evaluate options in the set Q. In A star algorithm, we use the F value, which is an estimate. Okay, the F value can also be seen as an estimate, not never overestimating, but it can underestimate. But nonetheless, it is an estimate, of the shortest path through a particular vertex to the destination from the beginning point, from the starting point. So once we understand it is just an estimate, then we go like, well, we just want the one that looks the most promising, which is the one that has the smallest value. So that's why when we choose the C, in O, we basically just say, everything else in O should have an F value that is greater than or equal to the F value of whatever we are choosing. Okay. Now, this is also important to understand that we're using less than or equal to and not just less than, because they can all have the same value if that situation happens. So once we have identified which vertex in O is the most promising, then we have to get rid of it from O so that we don't have an infinite loop. So that O is now without the vertex C. And then we have something that also resembles what Dijkstra's algorithm has, except in this case, in Dijkstra's algorithm, we look at all the incoming edges of the selected vertex. But in the case of the A star algorithm, we flip the direction. So we look at all the outgoing vertices from the vertex that we have chosen. So in this case, we look at all the one edge neighbors and of C. Okay, that's just another way to say they're neighbors. They're connected to C using one outgoing edge from C. That's basically what it's saying. And this time, I could have done the same thing with Dijkstra's algorithm to use a local temporary variable to store a particular value. So let's look at T and see what it actually means. It really is just G of C plus D of Cn. In other words, I know the shortest path from the starting point to vertex C already. Okay, that's G of C. So if I just add this edge Cn, then it becomes the length of a path, not necessarily shorter, but it becomes the length of a path from the starting point to vertex n. And I sort it as t. So now I compare t against g of n. Now remember what g of n is. G of n is the length of what we currently know as the shortest path from the starting point to vertex n. So if t is less than g of n, that means, oh, we have just found a shorter path from the starting point to vertex n. That is the only time we need to do something. Okay, so this is analogous of um, finding a shorter path from a vertex to a destination in Dijkstra's algorithm, except the direction is opposite. So what we do here is very similar to what we do, except we don't have an E prime. I choose a slightly different way to represent the solution graph. So I just have a previous function, which is to remember how should I get to vertex n? You should get to vertex n through vertex c. That's what pref n gets c is representing. Okay, it's just saying it's basically a backward pointer to basically say in order to get to vertex n, how should I get to vertex n? Yep, you should use vertex c to get to vertex n. That's what this statement is saying. We also have to add vertex n to the set O because we have just found a shorter path from the starting point to vertex n. Maybe this will impact the vertices immediately connected to vertex n. So let's maybe we should explore those in a future iteration of the while loop. That is why we are adding n to the set O. Updating g of n and updating f of n kind of makes sense, right? Because we just say, well, we just found a shorter path. Let's go ahead and remember the length of that shorter path, which is g of n. So when this loop is all done, it doesn't give us a solution graph because there's no e prime this time. So we're gonna have to we have to construct a new set for e, and I call this e as x. Okay, because it is s is the starting point, x is the destination, and the way we construct it is we look at all the pref functions, or we look at all the previous, the backward pointers, And this time, to reconstruct, everything, it is typical that people would start with the destination, and then it asks, okay, what is the vertex right before the destination? Okay, and then what is the vertex right before that one? And then we track that all the way, hopefully, back to vertex S. All right, so that's the overview of the algorithm. And what we're going to do now is to reuse one of our examples, but I can't really reuse the exact example from today's illustration of Dijkstra's algorithm, because that one has two destinations. And Dijkstra's, the A star algorithm does not work well with multiple destinations. So what we'll do instead is we are going to use, there are ways to pretend that you have multiple destinations, because what you can do is you can have a virtual destination that has zero distance incoming edges from all the actual destinations to the virtual destination. So that way, you would it would emulate, okay, the ability to have multiple destinations. But you cannot have multiple starting points, because the algorithm, g of something, can only track, one single starting point and not multiple starting points. So from that perspective, the A star algorithm is quite different compared to the Dijkstra's algorithm. All right, so let's go ahead and start a new graph. And I'm going to switch to the tablet view and refresh that. There we go. So we'll go ahead and start with something that can potentially is designed to trick the A star algorithm. In other words, we're trying to trick the A star algorithm to visit things that is kind of like, well, at first glance, that seemed to be a good idea, but turns out not to be a very good idea. Okay. So we have a vertex S, which is our starting point. We have vertex X, which is our destination. And then we go, let's make one edge going from S to X. Okay. Now, obviously, if we are to trick the algorithm, this single edge really should not be the shortest path, right? Because otherwise, the algorithm says we're done. Okay. So we'll make this cost, has a distance of 10. Okay. And then we'll make another vertex here. Okay. Here's vertex B. And vertex S goes to vertex B, and then vertex B goes to the destination. And then we have vertex C over here, vertex D over here. Okay. All right. So we want, the shortest path to be S to C to D and then to X. Okay. So in other words, we want this path here to be the shortest path, but we want to trick the algorithm into thinking the other paths are shortest. Okay, so that we just go like, oh man, this doesn't work out. Okay, now we have to go explore that. Okay, so now to do that, I have to be careful, because we are starting from we start exploring from vertex S. So that means we have to basically say, that looks promising, and then only to find that it is not promising. So we'll give this one, this edge from S to B, a distance of 5, and we'll give this a distance of 3. And let's see. Oh, we want to trick it the other way, right? Okay, because I want to illustrate that you can go back to the starting point. You can revisit things several times in A star algorithm, and you can design the heuristic to make it as bad as possible. So, how are we going to do this? The single edge is not going to be an issue. It's basically an issue between the double edge and the triple edge path from the starting point to the destination. So we'll make this a 5, 4, and then we'll make this a 6, Well, the heuristic is really the issue here. So we don't need to, um, this can be a 4, this can be a 2, and a 2. Okay, so that will work. Okay, now we have to define the h value or the heuristic value. So we say, h of ax. Now this cannot be, it cannot exceed 10. It can be 10 exactly, because it cannot overestimate. Then we have a of, no, I take it back, because it cannot be, it has to be less than or equal to 8, because 8 is the actual length of the shortest path from a to x. From b to x, it can be less than or equal to 4. And then from c to x, it has to be less than or equal to 4. From d to x, it has to be less than or equal to 2. And from x to x, obviously that has to be 0. So now we look at the heuristic values and we ask, okay, how do we mess up the heuristic value to try to trick the A star algorithm to misguide it, basically? Okay, we know that ACDX is the shortest path, but we don't want it to find that path like right away. We want it to waste time to realize that, hey, SBX looks promising, but it doesn't pan out. Okay, so to make a SBX promising, this is probably the best we can do, right? Because now, by the time we get to SB, okay, the estimate is, oh, that path is going to be have a length of 5. That looks really promising. Okay, so that is how we try to make things as promising as it seems. From CD and CX, we want it to be as realistic as possible, which is a 4. From D to X, we also want it to be as realistic as possible, which is a 2. From A to X, the way we make it doesn't really matter, okay, because eventually the algorithm will find that it is 8. We cannot make it 10, okay? So the question is, why can't we make this 10? Because the heuristic value has to be less than or equal to the length of the actual shortest path, okay? So 10 is not going to work. 10 is an overestimate. So 8 is the highest value that we can use for h of ax. It can be 0, okay? Well, I mean, if it's 0, it doesn't really matter, okay? Because we are gonna, um, the f value of x is going to be somewhat realistic. Doesn't matter what we do. So let's put a 0 here, okay? Because it really doesn't matter, and this will make it very obvious why it does not matter. Okay. So now we have a graph ready, and we got about 15 minutes left. I think we have enough time to work this through. So I'm gonna put, yeah, I'm gonna put the trace below it this time. Okay, there we go. And we want to look at how the algorithm is going to start. So this time I'm going to have column headers, and then we will track um, those particular things, as we go. So we have the set O, which doesn't come into play until we get to, pretty late. So from the initialization perspective, we got a whole bunch of other things that we have to do. We got vertex C, okay, we got vertex N. Once again, those are only used inside the loop. So, the initialization is focusing mostly on other things, which would be the G value and the F value, and also the pref, okay, which is the previous. So we'll focus on these three. So the G value is a function, um, and anything other than the starting point, which is vertex S, is going to have a G value of infinity. In other words, we're saying, I'm not even sure that we can get to that vertex from the starting point until we actually find one, okay, until we find an actual path. So the G value is a set of two tuples where S is mapped to 0, but everybody else maps to infinity. So B is mapping to infinity, C maps to infinity, D maps to infinity, and X also maps to infinity. So that's what G is going to look like. F is kind of the same. Okay, so I'm just gonna copy and paste it, except that in the case of F, the F of S is not necessarily 0 because we have to add the heuristic value of the starting point to the destination, which in this case is 0. Okay, I chose it to be 0. So that's the only reason why the G value and the F value of the starting point are both zeros. Okay, in a realistic type of example, h of ax is not going to be 0. It's going to be some non-negative values, but it's also going to be, more likely it's going to be a positive value that is less than or equal to the actual length of the shortest path. So that's what column E is tracking. And then now we have column G, which is the pref. So everything has a previous of unknown. So we don't know the previous of S. The previous of B is unknown. C has an unknown previous. D has an unknown previous. Okay, I typed the wrong thing. I'll go back and fix it. And then X also has an unknown previous. So let me go back and change the INF because we are not talking about infinity here. We're talking about unknown. So UNK is the abbreviation of unknown. There we go. So now we have everything that we need to track in this algorithm. We also have a t, which is really just a temporary variable, but we'll give it a column too, just so that we have one column for every variable that we want to track. So we're going to start with O. Okay, so this is the initialization. O is going to start with the starting point, which is S. So the first thing we choose out of O is quite obvious. Okay, we don't have anything. There's nothing to there's nothing to compare because we only got one element in O, so it has to be the one that looks the most promising. Okay, so we choose S, and Q becomes empty at this point, and then we look at all the outgoing edges of S, and there are 3. So the first outgoing edge is going to X, right away, and in that case, we want to compute, okay, what is going to be G of X, okay, in this case. So G of X is going to be G of S, which is by definition 0 or by initialization 0, plus the edge, the distance of the edge Sx, which has a distance of 10. So that means t is going to be 10 in this case, and we're comparing 10 to infinity because x has had an initialized g value of infinity, and we go like, 10 is less than infinity. Okay, so let's go into the conditional statement or the then branch of the conditional statement, and we fix this and go like, okay, we found a shorter path from the starting point to the destination, and it has a length of 10. We also update the f value, which is the same as the g value plus the heuristic from whatever vertex that we are considering to the destination. H of xx has to be 0, so that means the f and the g value are the same when we are talking about x. The previous needs a more obvious update because the previous of x, one way to get to x is just from the starting point. So we have s here. But we got a few other things to do too. One more, actually, is to add a to the set O because we just found, I take it back, sorry. It should be x in here. We are putting x in the O because we just found a shorter path to the vertex x. In other words, the algorithm doesn't really have a special case for the destination. There's nothing special to do when the destination is in the set O. Okay, it just doesn't consider that as a special thing, which is correct because even though we just found a path from the starting point to the destination, it is quite obvious that it is not the shortest. So we don't want to do anything special just because the destination is in O. Then we look at other outgoing edges from S. The other one goes to B. Okay. So now we ask the question, Are we finding a shorter path to vertex B? The answer is yes, because t is 5 in this case. T is g of s plus h of bx. H of bx is 0. Nope, it doesn't even take h into consideration because we're only comparing the g value. So we're only considering the g value, which is infinity to begin with. It was initialized to infinity, but now it is 5. T is 5 because um, the g value of s is 0, and then the edge from s to b has a distance of 5. So the sum of those two is 5. So that means, yep, we just found a shorter path from the starting point to vertex b in this case. Let's go ahead and update that. So now we have the g value being 5. And we also need to update the f value. The f value in this case is 5 as well because h of bx is 0. I chose it to be 0 to misguide the A star algorithm. Okay, so that was intentional. The previous of b is going to be A. Okay, so the shortest path from the starting point to vertex B is going to be from vertex A. Okay, there we go. And we now have to add B to the set because we just found a shorter path to vertex B. So everything after vertex B may have a shorter path at this point. And then we have one more. We have vertex C here. So, once now it doesn't take as much explanation to know that the new g value of C is going to be 4 because we found that path. But the f value, okay, so this is the most interesting part, is the f value of C is not just 5, just 4, because we have to remember to add the heuristic value from C to X, and h of Cx is as realistic as it goes, which is 4. So we have 4 plus 4, which is 8 in this case. And then the previous of C is going to be A. This is really just a way so that we can track how do we get from the starting point to the destination. So CA is now an edge, or the previous of C is A. Okay, so if you look at Prev, it is kind of like reversed edges of the solution graph, but not quite, okay, because there's no such vertex as the unknown vertex. So it's not exact, those are not exactly edges, but they're sort of like reverse edges. But we also have to remember to add C to the set O. So now we are done with the for each loop that is nested inside the while loop. So we now get back to the outside of the while loop. So remember, we are not quitting only when O is empty. We can quit when there's nothing looking promising at all in O. So we now look at g of x. G of x is no longer infinity. G of x is now 10. And now we want to look at the f value of b and c and see if at least one of them has an f value that is less than 10. So we look at f of b, which is 5. We look at f of c, it is 8. Well, things are looking pretty good because they both look promising. They both, it looks like at this point that we can find a shortest path through b or c compared to the one that we have found from the starting point to the destination. So we get into the loop. But once we get into the loop, we have to compare the elements and then find out which one looks the most promising based on the f value. And you can say, hey, S looks the promising, but that's irrelevant because the vertex S is not even in O, so it's not we don't even bother to consider that. So we are only comparing the f value of B, C, and X. The one that looks the most promising is vertex B. So we look at vertex B now, and we look at all the outgoing edges of vertex B. There's only one, which is B to X. So now we look at the t value. The t value is the g value of b plus the distance of the edge bx. which is basically just 5 plus 4, which is 9. So we look at 9 and we say, well, did we just find a shorter path from the starting point to the destination? The answer is yes, because the length of the currently known shortest path to the destination has a length of 10, and we just found a path with a length of 9. So we get into the conditional statement, or the then branch of the conditional statement, and we update the g value of x to be 9, and we also have to update the f value. And the f value of the destination is really kind of boring, because the f value of a destination has to be equaling to the g value of the destination. So they're both 9. And now we have to go here and fix up something, because the previous of x is no longer s, it is now b. Okay, because we just found that the updated shortest path has b leading to x. But that means we have to add vertex x to O again. So technically speaking, x is added to the set, but realistically speaking, there's no change because x was in the set already. So we don't see an actual change, but it is technically updated when we quote unquote add x to the set. So that concludes the for each loop, which means we go back out to the while loop. So now that we are back to the while loop, I forgot one thing, by the way. I forgot to get rid of C in O. I keep forgetting to remove the thing that I am considering from the set O. So now we get back to the outer loop, which is the while loop, and then we ask the question, okay, is the condition of the while loop still true? Well, O is non-empty, all right? And the second question is, if I look at the f value of the elements in O, is there at least one vertex in O such that its f value is less than the g value of x? The g value of x is no longer 10, it is now 9. And the f value of c is 5. Oh, uh, is 8. It's 8. Sorry, I take it back. It is 8. But that's okay, because the f value of c is 8. It's still less than the g value of x, which is 9. So we get into the loop. When we get into the loop, we have to find the vertex that has the least f value. And currently, the within the elements in the set O, the one that has the least f value is vertex C. So now we choose vertex C, and then we look at its outgoing edge or outgoing edges if it has multiple. There's only one, which is D. And now we ask, well, what is the length of the path from the starting point through C to vertex D? So we look at G of C, which is 4, plus the distance of the edge CD, which is 2. 4 plus 2 is 6. And now we say, well, should we get into the then branch of the conditional statement? And the answer is yes, we should. Because if you look at the current G value of D, it is infinity. We have not found a path from the starting point to vertex D yet. And we just found one at this point. So yes, the answer is yes, we found quote unquote a shorter path. And the length of that path is 6. So now we have to update the f value as well. The f value of D is not the same as the G value, because the heuristic function sets going from D to the destination has an estimated distance of 2. Okay. Oops. It's 2 plus 6, so it should be 8. I said 2 and then I typed 2, but I really meant to type 6 plus 2, which is 8. And we also have to update the previous, because now we know in order to get to D, the previous vertex is going to be vertex C. And we have to add D to the set. Okay, so now we have XD, and I keep forgetting to remove the thing that I have already considered. Okay, so this has to be updated first, and then we have XD left. So that concludes the inner loop, the for loop. and then we get back to the while loop. So once again, in the while loop, we ask that question, um, is there a path that looks promising here? So we look at this and we look at g of x. G of x is still 9, which is here. And then we look at f of d, which is only 8. 8 is less than 9, so yeah, so there's something looking promising in the set O. So we get into the while loop. We try to choose between vertex x and vertex d based on their f values. F of x is 9, f of d is only 8, so d is more promising than x, so we choose d, and then we look at all the outgoing edges from d. There's only one, d only goes to x, and the length of the path through d to x from the starting point is basically g of d, which is 6, plus the distance of the edge dx, which is 2. 6 plus 2 is 8, so here we have 8 here. And now we have to say, yep, we found a shorter path to x. And the length of that shorter path is 8 as well. So we put 8 here. And of course, we also have to update the f value. Every time you change the g value, you have to change the f value. But for the destination, they are the same, guaranteed. And then we have to update the previous. And basically, we're saying, hey, to get to the destination, we are not going to go through B anymore. We're going to go through vertex D this time, okay? Because we're looking at the edge dx. And don't forget, we have to add vertex x back into the set, and I keep forgetting to remove the element that I have selected out of x, out of the set O. So I keep forgetting that. I apologize. So now we get out of the inner loop because there's only one edge to consider. There's only one outgoing edge from D to somewhere else. And let's see. Okay, so I have to kind of scroll up a little bit or move this up a little bit. It's okay to move it up at this point because there's no need to refer to the graph any further. Because by the time we get back to the outer loop, the first question is there any vertex in O, because O is not empty at this point, such that its f value is less than the g value of x? Well, x is the only thing left, right? So now we have to look at the f value of x, which is 8, versus the g value of x, which is also 8. 8 is less than 8 is false. So now we say, the while condition is false. We can now get out. So this is the trace corresponding to this particular problem. And we're over by 5 minutes, but I do want to finish the algorithm so that you guys can see what the solution is going to look like. So now that okay, I only have to focus on one thing. So I'm going to just copy that here, okay? So we only have to focus on the previous. Okay, the tablet just fell asleep. Here we go. Okay, so we have to focus on the previous. I'm just repeating what I have um, in the trace. So the previous has S unknown, BA, CA, DC, and XD. Okay, there we go. Okay, now we can switch to the graph entirely. So remember what I said, we just want to look at these as quote unquote reverse edges and put it into the graph or highlight those. And the idea is you want to start with the destination. In other words, some of these edges are kind of pointless because they're not really along a path from the starting point to the destination. I mean, you can put it into the graph, but it's not going to be helpful. So if we are going to start with the destination, which is XD, then we go like, to the shortest path from the starting point to the destination is going to have the edge XD. Okay, so XD is quote unquote highlighted at this point. And then we look at DC. So that means to get to D, we have to start from C. Okay, so we highlight this one. And then we ask, how do we get to C? Well, we go to C through A. So by the time we track all the way back to the starting point, we can stop because the other edge, which is BA, I mean, it's technically, in the previous, but this particular edge is pointless to us, okay, because it does not complete a path from the starting point to the destination. So that's why, we typically just kind of draw enough of the solution until we find a path and then we're done, okay? So this is an example of running the A star algorithm. One thing you can do if you want to practice is to change the heuristic of this particular example. Okay, so you basically want to change these H values so that they are the best estimate ever. So you start HAX to be 8, you start with HBX to be 4, and so on. Okay, you make the heuristic value as realistic as it goes, and then see what happens. Okay, you retrace the algorithm, and I guarantee you that it will look different. Okay, the trace is going to look different. Um, but I want you to do that. Okay, to find out how the algorithm is going to be different. So I'm going to do a screenshot. So this way, I can copy the graph into the text area of Discord so that you can have a starting point for a practice. Okay, paste it here. And it's not liking that because I was using, oh, okay, it just took time. Okay, so I would say change the H values to be as realistic as possible and retrace the algorithm. It is not a graded assignment. So on Thursday, I would go over this example as part of the review for the final exam. So the final exam is going to have a pretty heavy spin on Dijkstra and the A star algorithm, but it will also have some of the other material that we talked about after the second exam. And yes, I am halfway through your grading the second exam, but it takes a long time because I actually have to read all of the answers and evaluate, the correctness of each one. Um, and so far, after grading half of the class, I got 2 people getting perfect scores. So that's actually pretty good. And I expect to have it all done, before the end of today. All right. So are there any questions? Or is everybody already falling asleep? Like my tablet. Okay. All right. So I'll see. Need more sleep. Yeah, we all do, don't we? One thing I found out is, even though I have more time after COVID-19, I have just found other ways to sink all my time. Oh, it depends on whether you have younger children in the household, because with younger children in the household, yeah, okay, that's what I guessed. Yep, yep, I understand that. I have teenagers, so a little bit different. Alrighty. So I'll see you guys on Thursday. And on Thursday, we're going to have a quick review of the final exam. Um, and then next Thursday is going to be our final exam. And I will get the forms prepared so that you guys can declare what time slot you cannot make it to. All right. Well, thank you. And I'll see you guys on Thursday. Bye.